Yeah, now I found this very nice materials in one of your books that I have. If we want to do some mathematical formulation for integer problems, there are a few like guidelines or rule of thumbs that we can use. Now I will go through some of these. So suppose that x is a continuous variable and then y is a binary variable, 0 or 1, right? And then some typical logic propositions, like for example in this case, select at least one of y, right? So if we select one of y, the logic is that we have to sum all of the y, and then that has to be larger than or equal to 1, right? At least one of the y should be 1. And that's what it is. So we have y1, y2, y3, and so on and so forth. And then the summation of all of them should be larger than or equal to 1. Like for example, in this case, it's written in the minor or in this algebraic notation. The second one is that select exactly one of y. So that means sum of all y has to be equal to 1. Right? Exactly has to be 1. So all of these we sum and then equals to 1. And then another version is that select at most one of y. So sum of all the y's less than or equal to 1. So these three are basically closely related. This is then if and then if x is positive number, then y equal to 1. So we make it like here. So we introduce the big M, what they call it big M. And then this big M is then it has to be like the biggest value of x that x can achieve, right? So basically x less than or equal to the number of the biggest value of x, or the big M, multiplied by 1. So if x is then less than 0, and then this y has to be like 0. Right, so y doesn't really matter. But then if x is then positive, so if this then like for example 1.5, for example, so this 1.5, so y has no option other than 1 to make this equation feasible. So if this is 1.5 or maybe a million, and then y has to be 1. So a million less than or equal to m is then another million multiplied by 1. The other one is then if y1 is selected, then y2 is also selected. So that means if y2 larger than or equal to y1, because if this is then 1 and this has to be 1, right? But if this is 0, y2 can be 1 or 2. It also can be a 0 or 1. And then another version is that if y1 is not selected, so this is then the negation of y1. 1 minus y1, so that's the negation of y1, and then y2 is selected. So it's basically the same form. It's just like y1 is then here we put the negation of y1, and then select y1 or y2. I think it's basically this one. So it's either or. So y1 plus y2 equals to 1. And then there's also another one like this junction constraints. It's either or constraint. So if function 1 as a f1 as a function of x, so it's less than or equal to the m1, the big m1 for this function 1 multiplied by the negation of the y1. So if this function so if it's not y1, so for example, if it's like y1 equals to 1, so that means this whole thing is 0. If this whole thing is 0, and then this is going to be like has to be 0. And then if y1 is then 0, and then f1 has to be like a number, right? So all the other way around, if f1 is then a number and then y1 is then a 0, so it's a bit of like a the other way around. I would expect is then y1 and y2, but nonetheless, so y1 plus y2 equals to 1. So it's either or. So if we have like two constraints in this case, f1 and f2, two constraints, and we have to pick one of them, yeah. So it's either or constraint. Both constraint cannot happen. So this is then the formulation that we can write and utilize. And I think these are like yeah, this is more like repetitions of the previous slide. But then we can see this table below. So if the logical relation is then OR, and then the Boolean expression is then this P1 or Y1, or P2 or P3, and so on and so forth. And then the algebraic formulation is that it's 1 plus Y1 plus Y2, and so on and so forth, larger than or equal to 1 in this case. So they don't put like equal to 1 either or. It's just like at least 1 has to be like 1. And then the logical AND, so by P1 and P2 and P3 and so on and so forth, and then they put like here, so Y1 larger than or equal to 1, Y2 larger than or equal to 1, and so on and so forth. And then the implication, so if P1 then P2, if P1 then P2, and then the Boolean expression is then the negation of P1, so if not P1 or P2, so this is then the Boolean expression, and then the mathematical expression is then this one, because not P1 means 1 minus Y1, right? This is not P1, plus this OR is then the plus Y2, and then larger than or equal to 1 is following this form. And then the equivalence means an P1 if and only if P2, right? So it's the other way. The difference is that if P1 then P2, but then if not P1, well, P2 we don't know. Then this one is then P1 then P2, and P2 then P1, so it's the other way around. So then we can hear from this form, we can then make a negation of P1, so not P1 or P2, like in this case. So not P1 or P2, like this guy. And stays the same, and then P2 is then now the negation is then not P2 or P1, so this is basically equivalent of that one. And then this is Y1 equals to Y2, Y1 equals to Y2. So if Y1 is 1, Y2 is 2, 1, Y1 is 0, and then Y2 is also 0. And then exclusive OR, so this is then the exclusive OR, not the logical OR. So exactly is 1 is then true, and then the summation is then equals to 1, like we have had above. To convert some logics into math expressions like this, we have like these 3 steps to follow. So we replace the implication by its equivalent disjunction, right? So this disjunction, so we need to have the OR, So if P1 then P2, this is then equivalent to not P1 or P2. So this is then the equivalent disjunction. So this guy, if this then that. And then we move the negation inwards by applying this De Morgan's theorem. So if we have this not P1 and P2, so we put this not P1 or P2, like this case, or in this case, not P1 or P2, it means not P1 and not P2. Right? So we apply this theorem, and then we then distribute OR over the end. So if this is P1 and P2, in the bracket or P3, this is an equivalent of P1 or P3 and P2 and P3, because this is going to be like one constraint, right? And this is then the second constraint. So let's put this into examples. So consider the logic that we have. If the absorber theoretical part is selected, so if absorber is selected or membrane is selected, then we don't use cryogenic separation. Yeah. So if absorber is used or membrane is used, then do not use cryogenic separation. That's basically what it means. So if your PA is an absorber, M as membrane, and then CS is in cryogenic separation. So the logic will be if absorber is used or membrane is used, then cryogenic is not going to be used. Yeah. If A is used or membrane is used, then do not use cryogenic separation. So we remove this implication. Because this is an if this, yeah, we put this into one item. If this, then this, right? P1, then P2. So we put the negation, like in this case. So if this, then that. So the negation of the first one, and then we change to OR, and then the second one we keep it the same. So we negate the whole thing. So not P1, not absorber or membrane, or we state the constraint, not cryogenic separation. And then we apply the Morgan theorem. In this case, we put this in. So not PA, not absorber, and not membrane in the bracket, or not cryogenic separation. And then we distribute this all into N. So I'll put it here. So not PA or not cryogenic separation, and not membrane or cryogenic separate or not cryogenic separation. So this is then the first constraint. This is then the second constraint, because this is the end. So this guy, not PA or not PCS cryogenic. So not is then 1 minus, right? 1 minus A plus, this is plus, this is or, right? This is or becomes plus. So plus not cryogenic separation, 1 minus cryogenic separation, larger than or equal to 1. So this is then this constraint. And then the second one follows as well, 1 minus membrane plus 1 minus cryogenic separation is larger than or equal to 1. And then we arrange this, we get YA membrane plus cryogenic separation less than or equal to 1. So if this is 1, this cannot be 1. Yeah. Same goes to here, membrane. If membrane is 1, and then the cryogenic separation cannot be 1 as well. And then the second example, so I hope that was clear. If flash is selected, then membrane, then select distillation, not membrane. Yeah. So if you use flash, then use distillation, not membrane. So we can have this F. If F, then distillation and not membrane. Yeah, not membrane. So we remove the implication. So that means we negate this guy, not F, or, and then this guy stays the same, D and not M, right? And then because we don't have any the N is not outside of the or, so there is no Morgan theorem over here. So we can just simply make sure that this guy, not F, put into this column, into this bracket, and then this one plus there as well. So not F or D, and we can change it to N, right? Because we put here in the bracket, and not F or not M, right? So this, then we distribute the or already, and then we have N. So it means we have this one constraint. This is then the other constraint. Now not F or D. This is then equivalent, not F or D, is equivalent to like 1 minus F is then not F or D plus D larger than or equal to 1. So that one over here. And then we arrange this, we get the D minus F larger than or equals to 0. So this is then our first constraint. And this is the second constraint. Not F or not M is 1 minus F plus 1 minus M larger than or equals to 1. F plus M less than or equals to 1. So this is the second constraint. So I hope these two examples, and then the procedure to change this type of statement into mathematical equations can be helpful when we design our mathematical optimization formulation. So yeah, thank you.